An electrical engineer at Pacific Northwest National Labs. And this workshop, number 3, is going to discuss the testing of IEEE 1815.2 beyond UL 1741. So focus primarily on some of the more advanced functionality and the scheduling and point multiplexing use cases. So the agenda for today is we'll go over a very brief overview of UL 1741, IEEE 1547, really just showing you the standards because we just went through 2 workshops, which we'll link at the end of the presentation that go into depth on kind of more of the background. And then we'll briefly discuss or we'll go into IEEE 1850.2, the current standard that is out to ballot right now. So we'll also have a call of action, get out and vote for that, and walk through some of the advanced functionality. And then we'll introduce the scheduling and test coverage. And at the very end, we'll try to do a hands-on demonstration of combining controls. So I'll start us off with a set of controls, and hopefully we can get some interaction, and I'll have someone from the audience pick another control, and we can walk through the steps of creating the control for it and making sure that it will operate as intended. So beyond UL 1741 were IBR, inverter-based resources, and DER cross paths. So UL identifies a utility interactive product as kind of the combination of UL 1741, IEEE 1547 and 1547.1, and the modified UL 1741 SA. So these all are brought together and create a distributed energy resource, typically seen as residential in most of the implementations that like California Rule 21 will identify. IEEE 1815.2 combines the DER functionality, and since it is already a DNP3 using protocol standard, it pulls in a lot of the utility-facing functionality that they already want and are typically using with DNP3, which kind of fall under the IBR category. And that's where 1815 kind of sits in between these two realms of kind of transmissions facing, kind of distribution facing profile. So before we can get into how we can combine these functionalities, we need to have a decent understanding of what the control modes are and how they interact with each other. So in IEEE 1547, we have prioritization of DR responses, which tells you at the top, permit service that just allows you to connect. Tripping, this is for if there's a voltage deviation or frequency deviation that you need to disconnect from the system immediately. Ride through capability, so they don't disconnect too quickly though. And then we have kind of your curve-based controls, your volt watt, frequency watt modes, active power limit to make sure you stay within some type of bounds for the system, and then your voltage regulation, in that order. Now, control types can kind of fall into 3 main categories. You have a target. Your control is trying to get to a point. If a charge and discharge, you want to charge at 7 kilowatts or 7 megawatts, that is your target. You have modified controls. These controls seek to modify a previous target or just the existing power set point from whatever is currently available. So these are anything that's kind of a following tag on it, where you'll have like your droop controls and your load following, generation following, your power smoothing controls. And then you have your limits, which try to bind your control within some type of upper and lower bound. We also have precedence. So most inverter-based resources and DERs have 4-quadrant control. So if you are trying to do an active power control and a reactive power control, there's only so much you can have of each. Precedence dictates which one gets priority over the other. On the left, we have VAR before watts. This is saying you want your reactive power to have higher priority than your active power, um, indicated by a larger green Q arrow compared to the smaller P in blue. And then on the right, we have watts before VARs, which you want active power to have higher priority than reactive power. So far, this is all pretty straightforward stuff. Feel like most people are pretty familiar with these. Now we get into the table of compatibility between all of the advanced controls that are available within 1815.2. In the, let's go back. Highlighted in kind of the light red, we have our emergency controls. These are your voltage and frequency ride-throughs and your dynamic reactive current and dynamic volt-watt controls. You can see that they are all compatible with each other because these are at the top of the priority list. No matter what, these should be accessible to active within your controls if they've been set. Next, we have in blue the active power controls. This includes frequency watt, charge discharge for storage, coordinated charge discharge, which is similar, but it allows you to kind of pre-configure what you need in advance. Active power limit, active power following 1, 2, and 3. This is peak power limiting, load following, and generation following. Don't quote me on that order, I might have messed that up. We have automatic generation control, active power smoothing, volt watt, frequency watt curve, which is different than frequency watt, as it allows you to indicate that it's a set of curve. You point to a curve index, and that allows you to establish a more fine-tuned frequency watt curve than the base frequency watt control mode. We have in synthetic inertia and price signaling. Then when we get into the reactive controls, we have constant VAR function, fixed power factor, volt VAR control, watt VAR, and power factor correction. You'll notice that some of these modes have a P and an M. That stands for they're separated by priority. Sorry about that. Separated by priority, meaning that if a function exists, if the two functions exist, the higher priority function will be the active one and the other one will be disengaged. A red M is a mutually exclusive control. And mutually exclusive controls means they cannot be enabled at the same time. Once one has been enabled, if you try to enable the other, you will get an error. Primarily, the mutually exclusive controls fall under the dynamic reactive power modes and the dynamic active power modes. But we have chosen some of the dynamic active power modes to be just priority driven over mutually exclusive. And this is still something that is kind of up for debate. So if you're interested, please join the working group and we can have a healthy debate on the topic. So let's go through an example of all of the control modes. We'll give them a priority. The lowest value priority, it's kind of like golf, is better than highest value. So all of our emergencies will be the highest priority. We'll have in descending order frequency watt, charge, discharge, coordinated charge, discharge, active power, so on. And the reactive power constant var is the highest over power factor at the lowest. So looking at all of our controls active all at once at the very start, we can first step through and identify which ones are mutually exclusive. Frequency watt will be mutually exclusive with the frequency watt curve. Active power following is mutually exclusive with automatic generation control. Automatic generation control is mutually exclusive with charge discharge storage, active power following, active power smoothing, and volt watt. Constant var, volt var control, watt var control, and power factor correction. And the power factor, fixed power factor is mutually exclusive with the same ones. And then priority, active power limit, we can see. We'll go into the next slide because I think this will actually highlight things a little bit easier for you. So continuing with the example, let's choose one of the control modes. So for active power response, if we highlight the table, we can see the very first, if you can see my mouse, I was hoping I could have like a highlight. I cannot do a highlighter. The active power limit has a priority designation for active power following and active power limit, and then it's mutually exclusive with automatic generation control. Then continuing down, we have it has a priority conflict with active power smoothing, volt watt, frequency watt curve, and synthetic inertia, which are all highlighted over here on the left, or right, sorry. So if we take that active schedule, we'll go back into our list and start cutting out all of the mutually exclusive controls so we can thin down the list of what should be active. So going down in priority, frequency watt is the highest priority of our active power so far. We can see that frequency watt is mutually exclusive with frequency watt curve. So we'll cut frequency watt curve because it is mutually exclusive. Active power response is mutually exclusive with automatic generation control. Since that one is already higher, we'll just assume that we enabled this one and didn't enable this one. Automatic generation control was already cut, and then const var z, spelling typo, sorry about that, is mutually exclusive with volt var control, watt var, and power factor correction. So we'll cut out those three, leaving fixed power factor is the only one that's still available. So now that we've thinned out the mutually exclusives, we can thin out the priority. Charge discharge storage has a higher priority than coordinated charge discharge, so we'll remove that from the active list. Active power limit has a priority conflict with active power response, automatic generation control, active power following 1, 2, and 3, and active power smoothing and volt watt. So we'll remove those from the list. And that leaves us with our final active controls. Sorry about this. We have our emergency controls, voltage right through, frequency right through, dynamic reactive power, reactive current, and dynamic volt watt, frequency watt, charge discharge storage, active power limit, price signal, and constant vars. So you can see, combining all of those together, we end up with a much thinner list after we've applied all the mutually exclusive designations and the priority conflicts and remove them from the list. So now we can get into point multiplexing. So point multiplexing allows us to generate curves that our controls can use and to generate schedules for our various control modes so that they can dynamically change throughout the day without needing a constant update from our control station. Point multiplexing is pretty straightforward. If we have on the left this giant array of our point indexes, we say, okay, this chunk right here, which I've broken out into two, could be the curve or the schedule. This chunk can be multiplexed into n number of curves or n number of schedules, which is basically creating a matrix out of this little array that you would have, allowing you to have curve 1 to n or schedule 1, 2 through n. The curve points, I have a, a type, a number of points that you are trying to assign, the units for your x values, the units for your y values, and then up to 100 xy pairs for your curves. For our types, we have the various control modes, frequency watt, watt var, volt watt. We have a remain connected type, a temperature mode, price signal mode. These allow you to create your coordination between the various modes through a single interface. And then for our curve states, the BI 107 will either say it's referenced if it's reserved or if it's unused. For scheduling points, kind of similar. The scheduling has been broken into two versions. The older version, version 1, which has an identity priority associated with it. So not only do controls have priorities, these schedules themselves can have priorities. A type for the schedule, a start date, start time, a stop date and time, a repeat interval, and the repeat interval units. We'll go a little bit in depth on some of the repeat intervals. Most of them are straightforward, but I highlighted a few that can just clarify what they mean. And then same as the curves, we'll have a number of points for that schedule and a value for the schedule and a time offset for that schedule. Now, I don't know if anyone's seeing a value for a schedule and thinking, how can you schedule a control mode and just have a single value for that control mode? What if your control mode needs multiple values? Well, that's why we came up with version 2. We decided, hey, we don't want to just be able to enable and disable a control mode or just modify one single part of a control. And we definitely don't want to have multiple versions or multiple controls or schedules for one control. So let's do a single control that can modify multiple values within the schedule. So we've eliminated the type in the new version, and instead we have a value, a time offset. Those are the same, but we also have the context of action type if you're writing to a BO or an AO, and the action index. So BO 110, for example, or AO 88, if you're trying to set some specific control. So let's go through a little example, clarify the scheduling. We'll pick this active power limit, has 2 points. We have a max set point and a min set point. Those are in AO 87 and AO 88 respectively. So for version 1, we can see we need 2 schedules. We had AO 87 and AO 88. If we look at our list of available types, we can see 12 is AO 87, and that will fall under kind of in the threshold type of control. And we'll set the value to 1, time offset 0. This is offset from the start time of your schedule's configuration. I've taken that out of this slide just to make things a little bit easier to follow. And the second schedule, identity 2, type 13, is AO 88, value 50, time offset of 0. So these two are linked schedules to accomplish a single control on 2 values. Not great, but also this is a pretty simple example, so it's nothing crazy, but you can see how things could get a little bit more confusing by splitting the context of these schedules apart from the control that you're actually trying to accomplish. So moving to version 2. Version 2, we have one identity, 1. We have a value of 100, time offset 0, action type AO, action type index 87, value 2, 50, time offset 0, action type AO, action index 88. So that doesn't seem too bad. Wanted to highlight time offset 0, time offset 0. Unlike the previous control, where you were only modifying one value at one time offset, you can have multiple time offsets with the same offset within your control block. This allows you to schedule multiple controls at the same time offset, but it does give you more chance for mistakes. So you need to ensure that your outstation, it doesn't just stop at the first new time offset. You need to walk every time offset until you've reached a non-unique time offset that's new. So we briefly mentioned that we have repeating schedules, and that came in the form of a repeating schedule value and a repeating schedule units. So I wanted to pull out the same day from end units. If we were to say have a repeat schedule value of 1 and repeat on same day of the week, we would see Monday, January, and then it would repeat the next day of the week on the 5th in February, which is the first Monday of February. If we had same day from end, we'd have a repeat on Wednesday in January, and then it would repeat coincidentally on Wednesday. Oh, it should have been Thursday. This is my mistake. Repeat on Wednesday or Thursday in February. Sorry about that. The repeat schedules monthly is a little more straightforward. You want it to repeat in 1 month, it will repeat the following month on the same um, uh, index in the month. So just fall straightforward. And repeat schedules weekly on the day. These are where most of the controls, same day of the week, pick Monday, Tuesday, Wednesday, Thursday. It'll just repeat every Monday, Tuesday, Wednesday, or Thursday. And you can set your unit to 2, 3, 4, so it'll be every other, every third, every fourth, if you desire. The primary ones I would envision being implemented are schedules for weekdays and schedules for weekends, and then the repeat from end and repeat from beginning to capture some of those typical holidays where you can see dramatically different load profiles than your typical weekday and weekend profiles that you would see. Now, scheduling has quite a few states. Walking through the states, this is not the easiest diagram to kind of follow along with, but we have editing, submitting, validated, enabled, running, preempted, completed, expired, disabled, invalid, and error. So let's start with editing. You set your AO 3000 to your index. This says, hey, I want to do something with the schedule. Your outstation is going to be updating all of the points that are associated with that schedule from that point mutex that we discussed earlier. It has some internal memory that it's going to access to update those values from. And then it'll set your BI 3000 to show like, hey, I'm on the correct schedule. To submit a schedule, you set BO 3000 equal to 1. the outstation is going to um, store and set the select schedule to submitted, which is AI 3010, and BI is going to remain 0. Then for validation, if it was successful, the outstation sets BI 3000 to 1, validate it, and transfers to valid state 3. If it doesn't, then it's going to transfer to invalid state 9. Once it's validated, the outstation sets BI we just discussed. We go into enabled. The control station sets AO 3000 to desired schedule. Control station sets selected schedule enabled to enabled state. Outstation checks if the selected schedule is valid, if it's valid. And then the outstation selected schedule status, AI 310, becomes 4. Once we've started running on a schedule that is active, the select schedule must be valid and it must be enabled. The current time has to be later than or equal to the time to run, and the repeat criterias are met. The outstation sets the schedule status to running, and the schedule statuses, you can see 100 up to 100 schedule statuses. If it's not there, you have to select the schedule index to validate if that schedule is actually running or not. If we are to cycle a schedule, so the outstation transfers to cycle complete. If the schedule is periodic, that's when you would cycle. It transfers back to the enable state, and it awaits for its next time to run. If the schedule is not periodic, then it transfers from cycle complete to an expired state. Outstation is expired. It's done, and it needs to be modified. Go back into the editing mode to update and reset for a new control. In the disabled state, the control station selects the schedule index. The selected schedule not enabled BO 3000 equals 0. That's saying, hey, I don't want this to be active anymore. Then the schedule will be transferred to disable state, and the schedule will still go through the must go through the validation process again. Invalid. Outstation transfers the schedule to invalid state. The control station is informed via status event. If it is enabled, shows the selected schedule is enabled, shows not enabled, BI 3000 equals 0 for the selected schedule. If the selected schedule is valid, shows not valid, BI 3001 equals 0 for the selected schedule. And the outstation logs the type of invalidity. So that's kind of how you'd be able to backtrack for debugging purposes if the schedule went through this control state. And error state, the outstation transfers schedule to error state 11. The selected schedule is enabled, shows not enabled, BI 3000 equals 0. And if the selected schedule is valid, shows not validated, then it's going to log the error in the outstations logs. All right, that was a lot. Hopefully it gave you a good enough start on what schedules are, how the advanced control functionalities interact with each other. It did not go through all of the semantic points for the advanced controls. I did that on purpose because scheduling and multiplexing is kind of a dense topic on its own, and it is the most unique of the advanced functionalities that has been added. So going into this hands-on demonstration, if the chat can start putting out a control mode that they think would go well, that they would want to be scheduled in advance, something that they would want to repeat at some type of interval. Start typing those in chat, and I can pop out and we can start adding them. But scheduling has this pretty simple workflow. You choose which version you want to work on. We can do version 1 or version 2. I would prefer 2, as I've shown. By holding the context together, it makes the schedules a lot easier to implement. And then we need to determine if our schedules can actually be active together. So we'll make sure that we're only creating schedules that are not mutually exclusive, and that we ensure that the priorities of the schedules are in the correct order for our use case. And we can talk about the time sensitivity, so when the schedule needs to be active, when it's supposed to repeat, as well as location sensitive, why you would choose to have a certain schedule active at a certain time, or based off of a certain service you would expect given its location. The starting schedule I wanted to pull up was active power limit, because it's pretty easy to see 3 distinct use cases just from a single control mode. We would have peak solar. I could see wanting to make sure that your outstation or your DER is in a constantly charging minimum state during peak solar. I could see during peak power demand, trying to make sure that your DER is discharging at least some amount to reduce that peak demand. And during outside of those 2 times, I could see having a schedule where you just want to block it from discharging or charging too much. So I will pop out. Let's see if there's been any comments in chat. Great minds, Francis. We have active power limit, that was already picked, but we also have AGC and charge discharge
as lower priority.
as lower priority. All right, let's go ahead. I'll note those in this. So we have active power limit. Then we had lower priority AGC, and then followed by charge discharge charge. All right. Let's pull up. I've created a table. If there's no issues with choosing, I just want to go back to chat. Okay. I will choose the new schedule implementation. So the first schedule, active power limit, we'll give it, this identity could be auto-generated, but we'll set it to 1 just to correspond with its index to make things simple. We'll give it the highest priority for now, and rather than an actual date, we're going to say these are all going to start at the same time, and they're all going to end. This is not the actual values, but it'll be easier on the eyes. Start date. So the first and start time, oh, I wanted to do 0, just 0. Start time at 0, makes it pretty straightforward. And end date will go to for now. And end time will be also at 0. So this is a single day schedule that starts on the 1st and ends on the 2nd. We're ignoring which year in month, it's just the first. The repeat interval, would we like one of these to have a repeat interval within this day? Because that is also a capability. Your repeat interval can be seconds, minutes, hours.
For this example, probably not. I think what you'd want is eventually to have a repeat interval of, weekly versus weekend.
All right. So for this, I agree. I think repeating does take a little bit more mental effort, and it's definitely something you'd want to programmatically generate to make sure things are landing where you would actually expect them. So we'll maintain on the same day, no repeating. So active power, time offset, action type is AO. We have 87. We already went through this, that's why it's going to be a little bit easier. Value,
50.
50. Okay. And
That means
then
50 watts.
we're controlling light bulbs here.
Or megawatt. Oh, boy.
Yeah, there we go.
None of them are quite, yeah.
This is a really big battery installation. Okay, we got the next point 2, time offset 0, action type also AO. We have, what do you want for the minimum? If max is 50.
2.
2?
Or if you want, we can make it minus 20.
Okay. Give it kind of the middle of the road a little bit, skewed towards positive. That's good enough for me. So this gives us our first time frame for, let's say, the morning. We'll say time offset is hours, not the seconds, just to make it easier. So
Yeah.
this is in the middle of the night.
So just make the minus 20 into the value, not into the action index, which is 88.
Yep. Yes, that is quite true. There we go. Got ahead of myself. All right. So that gives us our first point for basically midnight. What would be, what? Should we have a noon schedule?
Yeah, so at 6 a.m., whatever 6 a.m. is, we can just say 6
We'll just
a.m.,
say
but it's
6. We'll
yeah.
do a 24-hour day, so just 6.
Yeah.
All right, so we have 6.
And that, let's say, goes down to 25. Just
25.
these are random numbers.
Yeah. So now we're skewing more towards charging. So let's flip it to 50. Does that sound good?
Minus 50 if you're.
Yeah, sorry, minus 50.
And that's a good point. It has to be less, otherwise it's not a minimum.
Yes.
Okay.
All right, and let's go one more.
So then at, let's say 4 p.m., you're now going to go into the reverse where you want as much power out as you can get. The sun is beginning to set. So you want, so let's
That is
make that 4
16.
p.m., 1600. And now let's say that maximum is 75 and the minimum is 0. You don't want any charging.
Fair enough. All right, and then that would carry us into the back up here. If we were to repeat, the next day would start back over there.
Yeah.
All right, so that gives us our first active power limit. AGC. I did pull up I had the
I
picks
don't
sheet
remember.
up. Let's pull up the picks. AGC. All right, so we have AGC
146.
146. So let's start here. AO 146. Let's actually type that correctly. Value.
Yeah, you could be running it, but it's just at a lower priority, and I think that's the point here. So the maximum could be 100. So the maximum.
Let's go 100.
Yeah.
This is actually a good use case of the two. So if these were directly active at the same time,
actually, it would be AO 154 for the maximum usable SOC. So instead of 146, what you really want to put in there is 154.
154. What
The
maximum
maximum,
usable?
yeah.
Oh, so you, rather than setting a target power, you just want to dictate what its SOC values would be for
Yeah,
this given
it's
range.
what you're basically saying is it's lower priority, but it can still be 100, and then the minimum is 153, and whatever the AO and
oh yeah, AO 153.
and then 153.
And let's say that you don't want to go
Under 20. Okay.
Yeah, you want some reserve capacity.
Yeah.
All right. Now this will be active for.
Yeah. It could be discharging as well, but let's just keep it simple for the moment. In other words, you could do AGC while discharging, because all you're doing is changing. That's a delta output or input, but let's just keep it this way for now. So the point here is that the priority, if you go up to the top, the priority, let's say, is 5, Now 5, because priority 1 is a higher priority than priority 5.
That sounds good to me. Would there be any case for modifying towards the end of the night to want even higher capacity for storage? Maybe not even toward the night.
We could, but I'm just
There's a
thinking.
potential. I think this gets the point across.
I think that's what we're doing. So is this clear to everybody, or is there some questions on
Please,
this?
yeah. Sorry, I meant to say, if you have questions, shoot them out whenever you got them. And I'll try to pull up the chat if anyone pops in. Otherwise, the next charge discharge, we can give charge discharge as slightly, let's 7.
Yeah, that's
slightly
reasonable.
lower priority. Same start times, no repeats. Oh, we forgot to put the number of points for our schedule. So we ended up with what?
6
24?
points.
Oh, yes.
Well, 6 points. Yeah.
6 total. This is 2 total. All right. Our charge discharge, we could control the active power target for within these. Oh, I clicked on it, but 93. So AO 93. So we would say, hey, we want to make sure, I would assume we would want to try to discharge before the sun came up and then charge while the sun was up.
Yeah, or more or less, yeah. So
So
then it would be charging minus something, minus 30.
yeah, I was gonna say, let's go with something to where the higher priority function will limit it.
Yeah, okay.
Then we can have, when's our next one? Our 6 a.m. The sun should start to come up. So I would assume we would want to try to start charging it up. We could set the charge to be wait, did I have it? I think I had it backwards.
You got it backwards, yeah.
Yeah. 30, and we'll set it to -30.
But it will be limited. Yeah, it will be limited by the higher priority one. No.
And then at the, really, I feel like you want to discharge before and charge up as much as you can during the sun, and then we would say, okay, and then at the 4 p.m., which is 1600, action type AO 93 value, we want to really shoot down that peak. And
yeah, so you can make it 100, but it still will be limited by whatever the
yeah. So all right, so this gives us 3 scheduled controls for our first day. We're saying act power limit, we don't want to go outside of these thresholds. We're we're setting what our usable range for our battery is for this specific DER. And here we're just scheduling it a very simple charge before noon, charge during noon, discharge after noon, or sorry, discharge before noon, charge during noon, discharge after noon.
And just number of points there would be 3. And yes. I would change the wording in row 1 of the spreadsheet. Instead of value 1, 2, and 3, I'd say schedule 1, 2, etc. Because
oh yeah, I just dragged over. Yeah, these are in distinct schedules.
Yeah, it's because value is, the same word as point number, the 4th point in the schedule. So I would say that, C1 is schedule number 1, D1 is schedule number 2. I would just change those words to make it clear. These are all schedules. Yeah.
We'll do this. Oh, that was perfect. There. 1, 2, 3, 4. All right. So if there's another control someone would like to pull in, another use case, or if there's something else you'd like to explore, now's the time. We have 9 more minutes, or any other questions.
Okay, somebody's typing. Clip loss capturing. You'll have to explain that.
Yeah, that sounds like a very specific use case.
So if I oversize the PV, right, and govern the inverter, what you could do is that oversized portion could be scheduled to pump into the batteries and do things that way. So you'd get kind of it's a double dip.
Yeah,
in essence.
yeah. Yeah, that's absolutely the case. I think it's just a matter of setting that as either part of a schedule. If you're going to schedule it, of course, only when the sun is, or when the PV is greater than
Yeah,
what you need to use it for elsewhere, whether it's for the um, building or house or export or whatever else. Yeah, you can set that the remainder will be used for charging the battery.
right. And
Yeah.
so that would just be controlled on the battery side. I mean, on the inverter side.
If there's a single inverter that's managing both the PV and the storage,
Yeah,
then yes, it would have to be. If there's separate, pieces of equipment, then it could be handled by the
right.
controller.
The
Yeah.
EMS. Okay.
But I think that does highlight the usage of scheduling to create these specific use cases where
Mhm.
you have a functionality you're attempting to create, clip loss capturing, and you have a bunch of controls that are available. You can create that with the available controls, and we believe most use cases can be created with the available controls through some boundaries, some targets, and some modifications.
Yeah, this would be generation following, which is one of the functions. You'd be
Yeah.
essentially following the generation with a certain target where you wouldn't do anything until in this case, the PV system has reached the target and is now generating more. And then you can say, oh, okay, then the battery would start charging to keep the PV system from exporting more. Instead of exporting more, it would start charging the battery. So that's
Yeah.
the generation following function.
Okay.
I did go through that in workshop number 2, if you want to go back and look at that.
So before we um, end, I did want to mention the Mesa membership offers entry to our working groups and committees. We're currently on a working group break right now, but after the 4th of July and everyone comes back from their extended holiday, we'll be picking back up with our continued implementations for our testing, functional testing. The membership options are listed for standard, small business, and joint for our Sunspec Modbus membership and individual strategic partners, as well as students, which I, attending Portland State University, was a student who participated, although not very much. I would say it was more I listened in and just kind of picked up on what was happening. And at the beginning, I said that IEEE 1815.2 is out for ballot. If you would like to participate, please sign up, submit your comments, and let us get this thing into a full standard so we can continue our mission for interoperability.
So just a note on that, it's the ballot pool is now open.
Ballot pool.
The
Thank you, Francis.
balloting will start as soon as IEEE has finished all of its dotting of I's and crossing of T's. But then there will be, I'm not quite sure how many weeks they will allow, but a number of weeks for comments. And then probably starting around fall or late August or September, we'll start responding and reading the comments and responding to them. And that could be, depending, a very interesting and possibly lengthy process to make sure that we respond well to all of the comments. So if you're also interested in responding to the comments and as well as making comments, if you join MESA, then you'll be able to respond to the comments as well as obviously anybody can join IEEE and make the comments.
Thank you for the clarification, Francis. Anything else from anyone else? All right. Well, thank you for attending, everyone. And I hope to see you in the work group or the balloting process.
Okay. Have a good next couple of weeks before we get back to our